Hello everyone, today we are going to continue talking about how we can implement hash tables in Python. We have seen that the cost of these methods, the get and set item, comes from the for loop that iterates over the elements in a bucket. So these are in the order of the size of the bucket. Again, the performance then, this is something that we've seen in the beginning of this unit, comes from its load factor, meaning that a high load factor involves long buckets. This means that we must iterate over more elements to search for a key, as we have seen in the previous slide. And this also means a lot of collisions, because if the load factor grows drastically, it reflects that the table is almost full. On the other hand, we have the quality of the hash function. If the hash function is not distributing well the elements, it will degrade the performance. We will talk more about that later. Here we have an example of how the load factor evolves. We start with an empty table. With the load factor 0, we can include, for example, 5 elements, then the load factor goes to 1. We can include 5 more elements with a total number of elements of 10, and then the load factor is 2, and then including 5 more elements with a load factor of 4, with a total number of elements of 20. In this case, we can see that the length of the buckets are getting larger. So this will impact the performance of the hash table. We can solve this performing what is called the rehashing. This involves creating a new table with more room for allocating buckets, for example, duplicating the positions, and then rehashing the content of the old table into this new table. Okay, this will reduce the load factor and allows us to keep a good performance in the hash table. This is the method that we are including in our implementation, where we create a new table with more room for buckets, and then we have to iterate for each bucket, and on each bucket we have to iterate and we have to rehash the elements again to include them into the new list. We can update then the set item method in order to include a new condition that controls that the load factor is under a certain threshold. In this case, if this is greater than 2, we can perform this resizing, duplicating its size. On the other hand, we have the distribution of the elements along the table, along the list that we are using. We can have a table that has an uniform distribution of elements with almost all buckets, with the length similar to the load factor, or a table that has a not uniform distribution of elements with many empty buckets and some buckets with a lot of elements. We can detect this situation using what is called the occupancy histogram. In this case, we have in the y-axis the number of buckets, and in the x-axis the buckets that has a particular number of elements. For example, here we have 1 bucket with 0 elements. We have 2 buckets with 1 element, 1 bucket with 2 elements, none with 3, and 1 with 4. If we plot this histogram for the tables that we have seen before, we get these histograms. In this case, this is the expected behavior, an histogram that reflects that almost all the buckets are around the load factor. This is a balanced hash table, and on the other hand, we have this bad behavior that we want to avoid, where almost all buckets are empty and just a few of them contains almost all the elements. This is the representation that we have seen before. So we want to obtain this instead of this. This involves studying how the hash function behaves and how this distributes the elements along the hash table. Thanks for watching and see you in the next video.